So when we talk about testing a claim about a mean, it's going to follow a similar approach. The only difference is we have a different test statistic, and because of that, we have a different distribution that we're going to use. And even further, as a result of that, it's a little bit more complicated to find p-values here. So we're actually going to have to utilize some online calculators to do the p-value method. So we're going to start out by going through the notation that we're going to be using, the requirements to use this particular type of hypothesis testing, and then the test statistic, and then we're just going to do a couple examples. So starting out with our notation, n is still representing the sample size, or however many trials you're doing. S is our sample standard deviation. So this is the standard deviation from the sample that you picked. X bar is our sample mean. And then again, depending on the book, you'll have slightly different notations. Ours uses mu sub x. So mu is the true mean. Mu sub x is basically representing the one from the claim. So it's not necessarily the true mean of the entire population, but it's the one that's from our claim. So we're going to call this still our population mean. But this number comes from the claim. So whatever hypothesis you are testing. We have two requirements to be able to do this. It's a little bit more lax than the last one. You still need a simple random sample, and then you need your population to be normally distributed, or you need the sample size to be bigger than 30. As long as one of those is true, you're good for the second requirement. They can both be true though. So when we were dealing with the mean, remember when we looked at that, those came from t distributions or the student t distribution. So our test statistic is going to follow that. So we call it t. You find this by taking your sample mean, subtracting your population mean, and then dividing by s over the square root of n. Now, in the case that you actually do know the true population standard deviation, then that test statistic is going to follow the standard normal distribution. But again, that's really unlikely that you know the population standard deviation, but not the true mean. So more often, when sigma is unknown, that's when we use our t distribution with that degree of freedom being one less than the sample size, okay? So like I said, the easier method to do by hand is going to be using the critical value method, because that's where we can utilize our chart, which is at the very end of this. So our chart helps us out depending on if we have one tail or two tail, we still have that symmetry. So this gives us the area of one tail, and we can figure out what that critical number is. Because of symmetry, if you need a two-tailed, these are the same value, just one positive, one negative. So if I'm going and testing a claim and I know what level I want it at, so say we want our alpha to be 1%, well, if it's one tail, then I would utilize this chart, and I would look at however many degrees of freedom. So this would correspond to the degree of freedom being 14. And then I know that my value, depending on if it's left tail or right tail, is 2.64 and negative 2.64. So you'd pick either one depending on whether it's a right tail test or left tail test. If it's two-tailed and you want the area between them to be 1%, you again just go to that right column with the degrees of freedom you want. And this creates those rejection regions. And you see, does your test statistic fall into any of those rejection regions? With the p-value method, again, that's where we're just going to have to utilize a calculator to see the area that's in that tail that you have. And it'll depend on if it's a one-tailed or two-tailed test. So I will link a good calculator for you. But again, by hand, typically the best thing to do is that critical value method. So let's try this example. We're told a credit card company claims that the mean credit card debt for individuals is greater than $4,500. You want to test this claim, and you find that a random sample of 25 cardholders has a mean credit card balance of $4,575 and a standard distribution or standard deviation of 520. At an alpha level significance of 0.5, you want to see, can you support this claim? Okay. So I'm going to start just by writing down all of these key pieces of information. Our claim is that the mean credit card debt is more than $4,500. Okay. So that does not involve equality. So this is going to be our alternate hypothesis, which means that our null hypothesis is the mean equaling 4,500, or in the case of using an inequality, the mean is less than or equal to 4,500. So as a result, the alternate leaves one interval, and it's the mean being greater. So when I go to draw that distribution, that gives us the mean being greater. It results in a right-tailed test. So anything that falls into that one area at a 5% confidence level is going to be significantly important, which means we reject that null hypothesis. And so in that case, there's evidence to support the alternate, which is the actual claim. So I want to go through and I want to state all of the values for everything. Our random sample is going to be 25, which means our degrees of freedom is one less. So we're going to use the row corresponding to 24 for degrees of freedom. Our sample mean is from those 25 individuals. There was a mean credit card debt of 4,575. Our sample standard deviation, they tell us, is 520. And then our mean that we're testing is 4,500. And then our significance level is going to be 5%. So regardless of the method that I'm going to use, I need to know my test statistic. So I'm going to go ahead and calculate that first. And then we'll go into each test separately. So our test statistic is T. It's the sample mean minus the population mean over the standard deviation divided by the square root of the sample size. So this will be 4,575 minus 4,500. Our sample standard deviation is 520, and our sample size is 25. So I'm going to trust this part you can plug into your calculator. You should get that this is about 0.721. So again, I want to start with the critical value method because I think that one is a lot easier to do by hand, and especially on a test when you don't have access to an online p-value calculator, this is really the only method that you can go through. So looking at that critical value method, we have a one-tailed test, and our alpha level is 0.05. So that means when I look at this distribution, and I have some critical cutoff value, I want this area to have a chance of 5%. So this alpha, or this area, should be 5%, okay? So I want to see what is this cutoff value down here. So the area in one tail is 0.05. So using the t-table, with our degrees of freedom equaling 24, we get that this critical t value is the following. Okay. So I need to go down to the bottom again. We're looking at the area in one tail being 5%. So that's going to be everything in this column. And I want my degrees of freedom to be 24. So I need to go all the way down to where degrees of freedom is 24. So my critical T value is 1.711. So going back up here, wherever it may be, here we go, is 1.711. Okay. So this cutoff value is exactly that. So if my test statistic falls in here, that it means it is significant. That tells me I'm going to reject the null hypothesis. But our test statistic is 0.721. And if I were to plot that, that's somewhere over here. Okay. So it does not fall into the rejection region. So what that means is we either going to reject or fail to reject. Since it's not in the rejection region, we fail to reject the null hypothesis. Okay. So what that means is my claim going back up here, I fail to reject this. It means I have no evidence to support my alternative. So there is not sufficient evidence to support the claim that our mean is greater than 4,500. Okay. Now I want to do exactly the same thing with the p-value method to show that you still get the same result. This one's just a little bit more annoying because here we need to use technology to find p. So if I draw a picture as to what's going on here, again, I've got symmetry on my side with t-distributions. Our test statistic we found to be 0.721. And so I want to figure out what is the area here. Okay. So whatever this is our p-value. So when you use an online calculator, you'll plug in your value of t. Your degrees of freedom is again 24 in this case. Our significance level is 5%. And this in particular is a one-tailed test. So again, I will link one for you, but I do have one pulled up. So this particular calculator comes from the social science statistics, but again, you can just search p-value from t-distribution and you'll see a bunch of options. I like this one because you can just enter the t-score. In this case, it's 0.721. Our degrees of freedom is going to be 24. You select whatever your significance level is, and ours is 0.5. And then from there, you can also click whether it's one-tailed or two-tailed. So in here, I've got everything entered. So I go ahead and calculate, and they tell me my p-value is going to be 0.238937. So p is exactly that. So because of this p-value is going to be greater than alpha. So that means our rejection region is smaller than the actual full area of that. So since P is greater than or equal to our alpha, we fail to reject the null hypothesis. So it's only when the area to the right of this is smaller than our significance level. So pretty much it guarantees that it falls within that critical region. Okay? So same result, but again, this is not something you can do by hand. You have to use technology. Excel has some stuff for it, but again, there's a lot of online calculators. Okay? So let's try one more, and this one's going to be a two-tailed test, because if you were to do a left-tailed test, it would be very, very similar. But two-tailed is a little bit more difficult just because there's more work you have to do as a result. So you'll see we'll do another example like this for standard deviation as well. But we're told the claim is that the weight of quarters made after 1964 have a mean equal to 5.67 grams as required by Mint specifications. The sample size is n equals 36, and the test statistic is t equals negative 2.738. Using a significance level of 0.05, we want to figure out if we can support this claim. Okay. So they did a bit of work for us. We don't know what the sample mean was. We don't know what the sample standard deviation of was. They already did that part and calculated the test statistic for us. So what I'm going to start is by looking at my claim. So here our claim is that the mean is equal to 5.670 grams. So when I go to find my null hypothesis, that has equality. So my null hypothesis is exactly my claim, which means the alternate is that the mean does not equal 5.670. So it's bigger or it's less than this amount. So the result is going to be a two-tailed test. We're going to need to calculate two regions. But again, thankfully, we have symmetry on our side. We are going to do both methods though, so you can see how to utilize it. So going through, our sample size is 36, which means our degrees of freedom is one less, which is 35. And they already calculated the test statistic being negative 2.738. So we're going to start with the critical value method. So in this case, we're going to have two critical values that come exactly from the symmetry. Sorry about that. So if I go ahead, we're going to use the chart or use the t-table to find the critical value. With a level of significance being 0.05, our degrees of freedom being 35, and this is a two-tailed test. So we're going to have two different rejection regions because those are going to be the things that are significant. We have one critical value here and another critical value here, which is the same, but the positive case. And these areas are identical. But if I fall into either of these, that's where we're going to reject the null hypothesis. Okay. which is our claim, okay? So using my chart, I've got a two-tailed test, and the area in those two tails is 5%. So I'm going to be using this column here. My degrees of freedom is 35. So I'm going to have to scroll down quite a bit, keep going. And here is my degrees of freedom being 35. So my critical value is 2.03, which means the other one is negative 2.03. Okay. So we get two values for these critical numbers. This is positive 2.030, and this other one is negative 2.030. So our test statistic, T, is negative 2.738. That does fall in the rejection region. So since our test statistic falls in the critical region or rejection region, we reject the null hypothesis. Okay. We are rejecting the null hypothesis, which is our claim. So that tells us there's sufficient evidence to warrant rejection that the mean of these quarters is 5.67 grams. Okay. So what we can say is there is sufficient evidence to warrant rejection of the claim that the mean weight of these quarters made after 1964 is equal to 5.67 grams. Okay. So again, we can do the same thing instead using the p-value method just to show you it results in the same thing. You again need to use an online calculator. Where our specifications is our test statistic is negative 2.738. Our alpha level is 5%. Our degrees of freedom is 35. And this is a two-tailed test. So the specific calculator that I'm going to show gives you the total value of P, which is the area on the left and right. But here our test statistic is negative 2.738. So it's also finding the area over here too, corresponding to T being positive 2.738. So this area here on the right side would be P over 2, and this area would also be P over 2. So you can do a one-tailed test and then double it, or again, you can just do a two-tailed test and it's going to give you this total area, which is what we want. So using that online calculator, we're going to find our value of P. So using the same one, I now have to put in my new test score. This is going to be negative 2.738. Our degrees of freedom is 35. We still have a 5% significance, but it is now a two-tailed test. So in this case, our p-value is 0.009625. Okay. So what happens is the area outside this test statistic is smaller than our value of alpha, which is 5%. So that means we're going to reject that null hypothesis. So no longer need this. But here, since our value of P is less than alpha, which is 5%, we reject the null hypothesis, which still gives you exactly the same conclusion. There's sufficient evidence to warrant rejection of that claim that our mean is equal to 5.670 grams, okay?